So first of all, brief outline what I will be talking about. So I will give a brief recap of the idea of causal discovery, then bit into the background of what we wanted to look into with this method, then some first results and brief conclusion. So first of all, what is causal discovery? So it basically is the idea that if you have two or more variables, they might be correlated, but there might not always be a causal relationship between them. So one of the classic examples is you have ice cream sales and number of people swimming in the lake, and they would be correlated, but actually it's not that they are causally related, but the confounder in that case would be the weather. So there are several different mechanisms which can create such spurious relations, or even if you find if there are two variables that are causally related, it might not be possible, or yeah, just from a simple correlation analysis, you might not know which variable actually causes changes in which. So yeah, in which direction the causal link goes, so to say. Yes, and there's several methods how to create causal graphs, or yeah, from system of time series in this case. And the one that we use is the diagramite package, and specifically the algorithm TCMCA+. It is called, and it basically lets you, or it helps you find causal graphs from time series data. So for example, here we have three different time series of three different variables, which might be some proxies of physical processes, or yeah, just temperature data, whatever. So yeah, let's say you have your raw data, you can plug it into ESM-Waldtool or whatever, then get these time series which you plug into this algorithm. And the thing is, why you need pre-processing is that there are some assumptions which this algorithm is based on. For example, stationarity is one. So if you have seasonal cycles, you need to remove them, for example. So you would calculate monthly anomalies, for example. And also, yeah, you would detrend your data maybe. And also there's one other assumption which is quite prominent and sometimes problematic, is that it assumes, so TCMCA+, or what I think any of these algorithms in this package assumes causal sufficiency, which basically means that it assumes you include all relevant variables that might have some influence on some variable in your graph, that all are included. There's no confounder outside of the system, so to say, which is problematic in a system such as the climate system, which is very complex and you have a lot of different variables. But yeah, as also sometimes is the case with statistical methods, you might violate some assumptions slightly and hope that the results still are useful, because otherwise it's sometimes not possible. I mean, if you would try to actually include all variables that are relevant, you would just get a huge graph which you probably can't interpret anymore. But what this method then gives you, or this algorithm, is this such a link. So you have such a graph which with different links. So for example, these curved links are time-lagged links. You have contemporaneous links, which are the straight links, and then you have the color, which indicates the strength and the direction. So blue would be a negative link, and red positive. And also what will be relevant later on is that in the approach that I used, you will also have a width or thickness of the links, which is if you use several data sets, or in this case grid cells, it will tell you width of the link in how many cases of the different time series you use, so to say, this link appears. And so to the background a little bit, so the idea that I tried to look a bit into is this from a already fairly old paper. But the idea is basically that if you have these eddies, so these mesoscale features here, that they influence the air-sea interactions or the ocean-atmosphere exchanges. So, for example, here you have this anticyclone, so this is for the southern hemisphere. And this indicates here that in this anticyclone, you have, which is the same as here, you have this higher SST in the core of this eddy, which then causes anomalous heat flux from the ocean to the atmosphere, and then also changes the atmospheric circulation at this scale, and thereby might also influence precipitation. And so the opposite is true for the cyclonic eddy here. And what is also in there is that you have this wind speed, change in wind speed above these eddies. And also another thing that I added here is because we use this, so to say, as a proxy for the eddy in the model data for the eddies. So this is the sea surface height, which is elevated in these anticyclonic eddies and lower in the cyclonic eddies. So this is the basic idea. And what we did then is to take monthly anomalies of the summarized EERIE data and also of the ORAS-5 reanalysis. We took a fairly large area here, so from 50 west to 150 east, 60 south to 50 south. So this is just to illustrate the area basically, but this shows the climatology of sea surface height, but it's not that relevant. And so in this algorithm we took, we chose these parameters. So the maximum time lag is 1 month. Of course, that's already quite a lot for these processes actually. Then PC alpha, it's basically the confidence level, which is a bit high, but otherwise, if you use these individual grid cells, sometimes the algorithm doesn't find that many links if you're too strict here. And then this is the conditional independence test, so robust partial correlation test, which the algorithm uses to tease apart the different causal relationships. The variables that we use here is the zonal wind stress. So always detrended anomalies, sea surface temperature, sea surface height, and the net downward heat flux. And what we did is we took 256 samples of 42 grid cells for the higher resolution data, and a bit less grid cells to save some computational error, resources, and also to represent more or less the same area in total as with the high resolution. Took 7 grid cells per sample, and the 256 I took because I parallelized it that way to use to run all of these samples on one core on Levante. Basically what it calculates is an aggregate graph across these 265 samples, and each of these samples consists of 42 grid cells themselves. Okay, so the results look like this. So first, maybe let's look into the reanalysis data here. So this is RS5. And what you see is, for example, this fairly, so I think I will only focus on the links that have some color at least, because these very vague ones here, I don't know. I mean, sometimes they might also be interesting, but yeah, let's look at the older ones first. So here we have this quite strong connection between sea surface height or sea surface height influencing sea surface temperature. And for the heat flux, we have the sea surface temperature actually having a negative contemporaneous influence on the heat flux in this system, and the SSH has a negative influence on the heat flux. And which two links that are very persistent across all scales, what I will show you also in a minute, is this link here between wind stress and SST. So so this is basically probably is related to evaporative cooling and mixing of the upper ocean due to the wind stress. But what's also visible is this conflicting link here between heat flux and wind stress, and this is actually found in all of those. I think it might be related to the fact that actually this should go along. The wind stress should actually also influence the heat flux, and then I think the algorithm has some trouble with this lower part here, so these connections between wind stress, heat flux, and SST. But yeah, and what's interesting is, so if we think about what I told you earlier on this theoretical background, so to say, is that here we find this actually this decreasing heat flux with higher SSTs, which is what would fit to the theory. So we have, if we say this is a proxy for higher, for anticyclonic eddies, and we have this anomalous heat flux out of the ocean, this would be consistent with that. And if we look at the models, we see that, for example, the SST and heat flux links look different in the sense that at least this one here is missing. So this contemporaneous negative influence of the SST to the heat flux. And another thing that is interesting individually for these models is that, for example, IFS FESOM exhibits this link from SSH to the wind stress, which we also would have expected from theory, that you have this higher SSH, so as a proxy for the anticyclonic eddies, it increases the wind stress or the wind speed. And for ICANN, we have this fairly strong link between SSH and the heat flux, also this negative one, which makes sense, yeah. Then I also did the same with first regridding the results, so to look at what kind of information is lost when we, so to say, blur out these mesoscale features more. And what you see is that these links here, so for example, this SSA wind stress link disappears. And it also is visible that, now we have conflicting link here, and this link here disappears, so the SSH heat flux. So these mesoscale features that you might want to interpret from these graphs somewhat disappear. And then I also did it for some CMIP type models from the same family, let's say, as the EERIE models, just to see what they show. So I took this AVI, so from CMIP 6, AVI ESM low resolution and ICANN ESM low resolution. And here you actually see that this connection between heat flux and SSH is the other way around as in the as well as the opposite sign and direction compared to AURA S5. Also this heat flux link here to the SSH. And ICANN ESM looks quite strange. So we have this very strong link here. What I forgot to mention, what might also be relevant, but it's not that that interesting here, but it's that this color of these circles here actually is the autocorrelation of the individual variables. So SST always is very highly autocorrelated in these time series. But here the SSH also is very autocorrelated, and the main link you find is this between SSH and SST here. So this is a bit different from the others. Okay, to wrap it up, so there are actually significant differences between these causal graphs when we look at this CMIP models and the EERIE models. And it seems that some of these RC coupling features that you might expect are to some degree also captured by these causal graph, and so seemingly also by the models. And some next steps to refine this analysis might be to change the setup somewhat, to maybe look at smaller areas where you also maybe more focus on areas with more eddy activity, for example, to get stronger links maybe for these mesoscale features. Then also an idea would be to use observational data, although I'm not aware whether there's a very good observational data set for these atmosphere ocean heat fluxes, but the problem is that with AURA S5 you're a bit restricted because it doesn't have these variables like rain or clouds, which might be also interesting. So you would need to go to some atmospheric analysis and stitch that together. But on the other hand, it might also be a good idea to use observational data for these variables, and maybe include, as I said, other variables like also ocean velocity or rain, cloud fraction, whatever. But that's basically what I wanted to tell you, and maybe some parts were a bit unclear, so I'm happy to take questions now.
So thank you. So my name's Bobby. I'm going to talk to you about the piece of work we've been doing. So this is all, as I've talked before, it's all towards using machine learning atmospheres to perform a coupled spin up with a physical ocean. And so these are just two pieces of work that we're doing on the way to that goal. So the first one is seasonal forecasting with GenCast. So that is basically, there's something we've written up already. It's on the archive. So I'll just get into that. So the idea is that, as I said before, it's a precursor to being able to couple a dynamical ocean to an atmosphere, so that we can make. But as a first step in that, it's kind of good to see if these models that are trained at short timescales, when you couple when you run them out to longer timescales, do they display the behavior that they're responding to the ocean appropriately? It's also interesting for other ways, because it's interesting to see how these models like GenCast, which have been trained over, to predict at a very short time scale, how that extends to predicting at longer time scales. Always interesting to take these models outside their comfort zone to see if we can identify different biases that we can improve the models with. And as I said, it's interesting to see how investigate how these models kind of respond to the slower Earth system components like the ocean. So for those of you who aren't aware, we're using this model called GenCast, which is a stochastic generative machine learning model. It's what's called a diffusion model. It has we're using the 1 degree model partly because we couldn't fit the quarter degree model onto our GPU. It's at 12-hour time steps, which is a little bit longer than a lot of other machine learning models, like GrapHcast, for example. And I think that's mainly because this diffusion model is a little bit more expensive to run than something like GrapHcast. It does take in inputs like sea surface temperature, which is great because that's what we need. Although it's good to note that it doesn't take sea ice inputs. So we'll maybe talk about that later. And in general, there have been other people looking at seasonal forecasting with machine learning. I'd say there's kind of, roughly speaking, there's two approaches. There's what I would call the direct approach, where you directly predict, say, 2-meter temperature, the seasonal forecast of 2-meter temperature, so you don't have to predict anything in between, you just directly predict it. So there's definitely some work on that kind of for a while, but more recently there's been some work which what we're interested in is what I'd call the autoregressive approach, which is where you take a model that has, say, hourly or 6-hourly, 12-hourly time steps, and you roll it out from 0 to seasonal, for 4 months, and you look at the overall average seasonal forecasting from that. So there's been work on that relatively recently with different models. So Chris Kent et al. Used the ACE2 model with the prescribed SSTs. And there's been another one with neural DCM. The neural DCM one was actually more focused on storms, and so it was a little bit different, but the ACE2 one was similar to what we're doing. It's over the boreal winter. Yeah, so they're both using prescribed SSTs. I think what's interesting as well is that ACE2 is not a stochastic model, so they create ensembles using lagged, they do lagged ensembles. Neural GCM, also they create ensembles using a kind of perturbed initial condition. So it's interesting as well because GenCast is kind of more fundamentally stochastic. So could be we could see some difference there. So yeah, there's two setups we have, which is the first one is we just take the SST anomaly at the 1st of November, which is common, which is what they've done in the ACE2 and the Neuro GCM paper, and we just persist that SST anomaly over the SST climatology for the 4 months. So that's kind of the closest we can get to having a forecast without having a real coupled ocean or some kind of realistic ocean. We also have a forced one, so we're just forcing with reanalysis SSTs. And that's just because we want to see if the errors in GenCast are due to maybe missing some realistic ocean variability or a realistic representation of the ocean. So we initialize on 1st of November and rolling out to the 1st of March. We've done this for 30 years and for a 20-member ensemble. It's worth noting the 20 members it's not necessarily, if they were doing assessment of something like CES5 and East MWF, I think they'd be doing something more like 50 ensembles, member ensembles. So, it's worth bearing that in mind when you look at some of the results later on. And we're validating against reanalysis because ERIE5, because that's what GenCast was trained on. We validate precipitation against an observation product, and we look at we compare with the CES5 seasonal forecast just to see what that looks like. And I think some of you probably know there's some of these years are within GenCast training set, but because that's been trained at very short timescales, we still regard, and we're giving it something like persisted SST anomalies and things like that. From my point of view, we still see it's kind of somewhat out of sample. So you wouldn't expect it to necessarily perform well at these long timescales. So to begin with, just look at some case studies of really strong La Nina and El Nino years. And so, yeah, you can see that here you just have top left is the observations, top right GenCast persisted, bottom left GenCast forced, and then Cs5. And just broadly speaking, looking at all these, you can see they're very similar. You know, even GenCast persisted picks up on a lot of the correct like wetting and drying over the Pacific and the maritime continent. There's definitely a few issues though. So you can see where over the Eastern Pacific, there's some kind of strange behavior there. There's a bit more wetting over the Hudson Bay and the Labrador Sea, and a bit more kind of wetting over the eastern coast of Australia. But I guess the interesting thing is if you look at the forced one, you can see how these problems go away. It's very hard seeing much difference between GenCast forced and Cs5. So it's kind of suggesting that GenCast is responding appropriately to the ocean, even though it's kind of not really trained at a very long time scale to predict that. And the same with El Nino. I think a similar story is that you can just, if you blur your eyes, you can see that these are all kind of very similar patterns. However, there are still differences with GenCast persisted. So it's definitely got some different behavior in the ocean, the eastern tropical Pacific and the Atlantic. But again, these are kind of really corrected by GenCast force. So it does seem to suggest that GenCast has kind of learned some of the right responses to these SST patterns. I don't think I've actually got time to do this, so I'm going to skip this slide. But we've also looked at a lot of things, and if you want to look at anything more detailed, just look at the please look at the preprint. But we've also looked a little bit at NAO prediction, so another kind of case study thing. In general, you can see that I think the main thing to look at are these correlations down here. So you can see that GenCast persisted has 0.27 compared to 0.20. I think at this number of ensemble members, I think it's just about. All you can say really is that these are kind of comparable. They have comparable skill at the NAO. I think you would expect to see these correlations increasing with higher ensemble members. That's been shown in other papers. Another interesting thing though is just seeing that the 2009 NAO, which was a very extreme one, it's interesting to see that both GenCast models do dip down quite significantly far below, the rest of the years. And so that's kind of interesting that for that really extreme case, they did manage to predict that. We've also looked at things like anomaly correlation coefficients. We have done this for many more variables, but just for the sake of time, I'm just showing you mean sea level pressure. So I think the main plot to look at is the bottom right here. That's just the difference between Cs5 ACC and GenCast persisted ACC. And so as you might expect, there's a lot of red where Cs5 is doing much better, but also there's lots of blue as well where GenCast persisted in this case is doing better. So it's kind of interesting to see that broadly speaking over the tropics, you do see a lot of improvement, Cs5 doing a lot better, but over the extratropics, actually, there's some kind of suggestion that GenCast persisted is picking up some skill where maybe Cs5 isn't. Particularly, you can see the North Atlantic there. There's like a little bit of an improvement, and that could be connected. That's obviously going to be connected to the slight difference in NAO skill. But I think what's interesting as well, though, is that even if you look at these things for 2 meter temperature, where because GenCast doesn't take any sea ice as input, it's interesting that there isn't GenCast persisted still does achieve kind of comparable skill over sea ice where you might not expect it to. So that's quite interesting. We've also looked at reliability. So as I mentioned before, because GenCast is a fundamentally stochastic model, unlike ACE2 and GCM. So we really want to make sure that it makes reliable predictions. And so this kind of just summarizes what we see for many of the variables in that if you look on the left-hand column, which is GenCast persisted for the lower tercile and upper tercile for 2 meter temperature, you can see that it basically just kind of lies along the line of no skill, which is this kind of solid line just off the diagonal there. But then when you move to GenCast force, so it has a kind of realistic representation of the ocean, that increases much more as the reliability gets much closer to the dashed line of perfect reliability. and gets kind of comparable to the reliability of CS5, particularly for the upper tercile. So that's kind of generally what we see, is that for a lot of the variables, GenCast persisted basically lies along the no skill line, but the other ones improve much more to the diagonal reliability line. So that's the first half of what I'm going to talk about. And in summary, as I said, I've just kind of rushed through it because I've got two things to talk about. But if you're interested in more results, please do check out the preprint. But I think the main take homes is that GenCast, it performed surprisingly well at doing the seasonal forecasting, given that it was only trained to predict, medium rain forecasting, so up to 10 days. And we're rolling out for 4 months. It's kind of, and it doesn't have sea ice as an input and doesn't have any land inputs. It's kind of, I think it's pretty surprising that it can do that well. So it's obviously can be trained quite well. And also, I think it suggests that were we to couple GenCast to a realistic ocean, we could expect to see a bit of an improvement in the skill, given the way that GenCast forced, the skill of GenCast force has improved. And again, the reliability just shows that I think that a lot of the GenCasts, a lot of the kind of miscalibration of GenCast probability distributions, a lot of that can be corrected by kind of having realistic ocean variability. And it's also worth noting, as like with a lot of machine learning models, these are really relatively quick. So it's 30 minutes for a 40-month rollout, which would be, I think, for the comparable resolution model of the IFS would be about 2.5 hours or something like that, which is still not, it's not as drastic an improvement as other models such as GrantAgreement, which are a lot faster than the diffusion model, but still quite an improvement. So I'm going to just move on now to the kind of next thing we've been working on, or the kind of the next step. So this is coupling a machine learning atmospheric model to NEMO, a dynamical ocean. And the reason we're doing that is, as I said before, we're really interested in coupling improving the efficiency of ocean spin-up, coupled ocean spin-up. So to do that, our approach is to replace the atmosphere with machine learning atmosphere, and that kind of almost effectively halves the compute resources you need to do the spin-up. But also, I think just generally, as we think about how we perform climate emulation with machine learning models, we have to be able to couple. It's not. I guess it's not really clear what's going to happen in this space, and how we're going to couple, say, atmospheric models to ocean models. So it's kind of interesting to just explore this space. There's been other people that have been looking at it from a different point of view. So that, one way you can think about doing this is taking a machine learning atmosphere and a machine learning ocean and train them both separately and train them together as well. And then you have a kind of full machine learning Earth system model. And that's what they've done in a very recent paper by Duncan et al., which they call Samudra. So it's a combination of Samudra, which is an ocean model, and ACE2, which is the atmosphere, and they train them separately, and then they fine-tune them together, and then they roll it out. So I think the upside is this, that when you get this working, it's really incredibly fast. I think it's something like 800 simulated years per day, or perhaps more than that. I think the downside is that you obviously have to you need the resources to be able to either train, but perhaps train both models, but at least fine-tune both models to work together. And I think that I'm not sure exactly. So Samudra, the version of Samudra they used here has a 5-day time step as well. I'm not sure if there's a reason that it couldn't be lower, but that's the current setup could be missing some kind of variability there. So our approach, because we don't have the resources to retrain Samudra or ACE, so we just take a model off the shelf. And so I think the advantage of this is that it's much more like we don't have to do any retraining, and it's an interesting out of sample test. So like if we take these models, it's interesting to see if we can use these models in the way that conventional climate models would be used, and just see how they behave with inputs they maybe haven't seen before. But obviously the downside is it's not as fast because we all still have a dynamical ocean to run, and it's a little bit more cumbersome in many ways to implement because we have to figure out how to couple these things together. So we're looking at coupling ACE2 to NEMO currently. And so the challenges you could probably think of is that NEMO runs on many CPUs, whilst ACE2 runs on a GPU. And most HPC environments that at least that I'm using, you can't run a GPU job and a multiple CPU job within the same MPI environment, so you can't get them to kind of communicate. or at least not in a very kind of straightforward sense. Also, ACE2 doesn't, the model, the version of ACE2 that's kind of publicly available doesn't actually produce all of the fluxes that NEMO requires. It doesn't produce things like wind fluxes. And so we have to kind of calculate some of those fluxes ourselves. And obviously, ACE2 runs at a 6-hour model time step. So NEMO obviously not runs at much smaller time step. So we have to make sure that there's not some kind of problem with that mismatch and that the fluxes that NEMO are getting are still kind of up to date and realistic. So for the first challenge, because NEMO is CPU intensive and ACE runs on GPUs, we've been using a kind of, the best solution we could come to is just, is basically taking, I'll just talk you through this diagram. So we have like, we basically run NEMO on the CPU node, so that's what these red dashed line indicate. And NEMO runs as it normally does, and we're just running on 2 nodes. And it communicates via Oasis, which is the kind of built-in coupling package. It communicates via, we just kind of create this kind of router script that kind of intercepts those messages and sends messages back. And what we do is we just write all those the ocean variables to a scratch disk. And then meanwhile, the atmosphere, ACE, running on a GPU node, can poll that scratch disk. And when the atmospheric variables are available, it can pick them up, run itself forward for another time step, rewrite the atmospheric variables down. And so you have a little bit of like overhead here of like writing to scratch disk. It's not like necessarily, it's not actually, it's not the dominant overhead we have actually, but it's it's a little bit annoying. So obviously it's something we'll look to in the future, improve and come up with a nicer solution. But luckily for us though, there's Oasis has a Python wrapper, so we can use that already, and that means NEMO is communicating using Oasis, and it means it waits for responses and things like that, so everything's kind of nice and synchronized. The other challenge is obviously I said that ACE2 doesn't produce all the fluxes, so we've been using a package called ERIE flux code, which is basically is a Python implementation of the bulk formula that NEMO uses if you're using it in, say, like a forcing it with climatological variables or something like that. We also have to predict solid precipitation because NEMO wants solid precipitation, but ACE only predicts total precipitation. So we have some kind of heuristic model that just calculates solid precipitation based on the 2-minute temperature and the total precipitation. And that's just a little diagram we've got here. So yeah, ACE2, ACE2 using ERIE flux code to produce fluxes. So I'll just go on through some results. So so far we've run, I've run out to 80 years and it's stable. I mean, it could have gone for longer, but I've just stopped it. I've currently stopped at 70 years. So I'm currently running 1915s control runs and 1950s historical runs. So I've got multiple ensembles for each. So currently I've got about a 3-member ensemble for 1950s control and a 3-member ensemble for 1950s historical. And as you can see, we had a few problems we had to fix, such as instabilities in NEMO sea ice. So we had to kind of modify the way that the fluxes over the coastlines were behaving over the sea ice points. ACE2 has a bit of a problem with freshwater budget over long time scales, so we had to impose in NEMO the evaporation minus precipitation minus runoff is kind of conserved. And there are some kind of funny things going on with ACE2 fluxes over ice. So we had to switch to using the core bulk formula to calculate the those fluxes over ice. And I'm still kind of looking into kind of how we can improve those fluxes. But yeah, as you can see there, if you look at these time series, this is the 70-year historical run for just one ensemble member. You can see that it's relatively stable, so there's not necessarily that much drift in terms of things like 2-minute temperature. I also have things like sea surface height that are kind of just generally quite stable. So it's nice to see that it's kind of producing something that's pretty stable. Also, obviously worth checking that these are actually coupled. So this is here we're just regressing the we calculate the Nino 3.4 index over the ocean, and we correlate that we regress that onto the precipitation. And so you can see on the left here, that's ACE2 NEMO's precipitation response to Nino 3.4, and you can see that's very much similar to what you'd expect from ERA 5. So what I am working on is gathering the ECR3 data. So we've deliberately chosen the config for NEMO, which matches the CMIP6, so the high-res MIP Primavera run. So we have data for a control 1950s run, which we're comparing to now. So yeah, that's what we will be doing going forward, is kind of, rather than comparing with ERA 5, comparing with ECR3. And this is just also, the same. This is NEMO 3.4 index calculated for a single member ensemble, the single ensemble member. Just to demonstrate that there's this kind of coupled variability going on. Again, what we're going to be looking at here is probably looking at the spectra of these this NEMO 3.4 time series and seeing how that compares to ECR3 and ERA 5. So yeah, as I said, we've done a control run. We also have historical runs. So yeah, this is just the global 2-meter temperature showing here for the historical run in blue compared to ERA 5 in orange. I think the first thing to note is obviously there's a big gap, and having looked into that, it looks like there's actually quite a different, the initial conditions we have, which were provided by BSC from their runs, they seem to have a bit of a temperature difference compared to ERA 5 for the same period. So I think we'd expect a little bit of a gap. But you can also see the kind of trend seems very similar between ERA 5 and ACE2. So it's worth noting that ACE2 takes in greenhouse gas forcing, so you would expect it to still have some kind of the appropriate response to this. But it's just good to see that it's keeping that. Yeah. So I realize I've gone through a lot of stuff here, but I'll just summarize quickly what we've got, and maybe we've got time for some questions. So we've been looking at GenCast for seasonal forecasting. So GenCast using prescribed SSTs with 2 different setups, using forced SSTs or persisted anomalies. And so I think just generally that it shows surprisingly good skill for a model that hasn't been trained at all to predict over long timescales. And I think next step for that would be seasonal forecasting coupled to an ocean model. So in the work I've done with ACE2 coupled to NEMO, we also have got that working with GenCast coupled to NEMO. So that the problem we have is getting initial conditions for the correct period that would then allow us to do for NEMO, that would allow us to do seasonal forecasting with GenCast. And yeah, coupling ACE2 to NEMO, as I've showed you, we have a prototype that's up and running. We're currently just running as many years as possible over as many different ensemble members, and it seems to be stable for as long as we can run it. So next steps, we're going to be obviously analyzing all the ERC interactions, things like heat and freshwater budgets, try and figure out exactly why ACE2 can't, what's wrong with the freshwater budgets with ACE2. I'm also running ocean spin up. So I'm going to be running currently running the spin up with ACE2 coupled to NEMO. And then in the new year, we plan to take those spun up states and give them to BSC, where they will run their version of ECR3 with the same config for NEMO, and see what we'll compare the kind of drift and see how well ACE2 is doing at spinning up NEMO. And I think the long term, it'd be interesting to expand this to more models. So we're interested to do much more kind of multi-model work with things like AIFS, perhaps NeuralGCM. And as I said, coupled seasonal forecasting with GenCast or ACE2 or both perhaps would be really interesting to see if we can match the skill of some of the existing seasonal forecast models.
Any more questions? If not, I would like to make the advertisement for the next Storms Eddy and Science seminar on the, well, let me go to the page, in January, 19th of January. There are presentations from Dave Stockley using sequence accelerations to speed up ocean model physics spin up for climate simulations, and modeling groups will give an update on the EERIE phase 2 simulations.